We've learned that the reason atoms bond is to complete their valences so that they can become more stable. Oxidation numbers are used to keep track of how many electrons are lost or gained by each atom. Often they're the same as the charge of the ion. And we assign oxidation numbers by using a set of rules. Rule number 1 states that fluorine is always a -1 oxidation number when it's bonded to another element. This is the same as the charge of a fluoride ion. Rule number 2 states that oxygen's oxidation number is always -2, just as an oxide ion has a charge of -2, but there are a couple of exceptions. In peroxides, oxygen will have an oxidation number of -1. And when oxygen bonds to fluorine, its oxidation number will be a +2. So since fluorine is always -1 no matter what it's bonded to, and oxygen, when it's bonded to fluorine, we said would be a +2, then we would need 2 fluorines for these two elements to form a neutral compound, giving us the formula OF2 for oxygen difluoride. Rule number 3, hydrogen's oxidation number is always going to be a +1, just like when hydrogen forms a hydride ion, it has a charge of +1, but there is one exception to that also. In metal hydrides, that's hydrogen bonded to a metal or a metalloid, its oxidation number, hydrogen's oxidation number in that instance would be a -1. So let's look at a couple of examples. When hydrogen and oxygen bond together, their oxidation numbers are going to be a +1 on our hydrogen and a -2 on our oxygen. And so when hydrogen and oxygen bond in this instance, we would need 2 hydrogens for every oxygen to give us the neutral compound H2O. But remember that in peroxides, oxygen's oxidation is a -1. And the formula for hydrogen peroxide is H2O2. And so we have oxygen with a -1 oxidation number, and with hydrogen still having a +1 oxidation number. You can see that with the formula H2O2 for hydrogen peroxide, it makes sense that we end up with a neutral compound with 2 H's with a +2 total and 2 O's with a -2 total. Now, if hydrogen were to bond to sodium, which is a metal, it'll have an oxidation number of a -1. And our sodium will have an oxidation number of a +1, just like a sodium ion has a +1 charge. And so the formula for sodium hydride then would be NaH. Which leads us to the next rule, which is the group 1 metals are always going to have an oxidation number of +1, just like they have a charge for their ions of a +1. And the group 2 metals will always have an oxidation number of +2. And aluminum is always +3. Rule number 7 says that the sum of the oxidation numbers in a neutral compound is always 0. And rule number 8 says the sum of the oxidation numbers in a polyatomic ion is equal to the charge of the ion. Rule number 9 says that the oxidation number of an uncombined atom is 0. So anytime you have an element that is not bonded to anything else, then its oxidation number would be 0. So where you would have an oxidation number for sodium of a +1 when sodium is bonded to chlorine, if you had just plain sodium by itself not bonded to anything, its oxidation number would be 0. This is also true for our 7 diatomic molecules. Our next rule states that the oxidation number of a monoatomic ion is going to be equal to the charge of that ion. So for example, the formula for an oxide ion is O with a -2 charge. And so an oxide ion's oxidation number is also going to be a -2. And rule number 11 is what will cover us when we don't have a specific rule to attach to a particular atom. And it states that the oxidation number of the more electronegative atom in the molecule is the same as it would have if it were an ion. And I'll show you some examples of how rule number 11 would be used as well. Let's try a few of these out. Our first compound, CO2, or carbon dioxide. So we don't have a rule specifically that deals with carbon, but we do have a rule that deals with oxygen. And oxygen is always -2 unless it's in a peroxide or it's bonded to fluorine, neither of which is the case here. So if we know that our oxidation number on the oxygen then is a -2, and also that the sum of the oxidation numbers in a neutral compound has to equal 0, and since we have two oxygens, each with an oxidation number of -2, then we have a -4 on the oxygen portion of the compound. And since the oxidation numbers have to add up to 0 in the neutral compound, then that means that the oxidation number for the carbon must be equal to a +4. The next compound we will look at is calcium oxide. Now we do have a rule for calcium because we know that group 2 metals will always have an oxidation number of +2. And we know that oxygen's oxidation number in this instance is going to be a -2. In this instance, both of the oxidation numbers here are going to be the same as the charges would be on ions of calcium or oxygen. Here we have oxygen that is not bonded to anything else, so it is an uncombined element. And so any pure element will have an oxidation number then of 0. Let's look at what happens to the oxidation number of nitrogen in two different compounds. Here we have nitrous acid and here we have nitric acid. Our rule for hydrogen states that in this instance, since it's not bonded to a metal, the hydrogen will be +1. And there's only one hydrogen in this compound, so I'm going to bring that +1 down for our housekeeping. And since this is an acid, not a peroxide, the oxidation number for the oxygen in this compound is going to be a -2. And since we have two oxygens in the compound, then the total of the oxidation numbers in the compound will be a -4. Now, I don't have a rule for the nitrogen, but I know that the sum of these oxidation numbers must be 0 because this is a neutral compound. So that means that the oxidation number on my nitrogen must be +3. Now over here, my oxidation number for the hydrogen is going to be number +1. And the oxygen is going to be -2. But now we have 3 oxygens giving us a total of a -6, which means the oxidation number of the nitrogen is a +5. Also, you should note that these are the actual oxidation numbers. This is just the housekeeping that I use, my process to determine what the individual oxidation numbers are. So I hope this helps you to be able to determine oxidation numbers of elements on your own.